Yep. Okay, guys, I'm going to get started here. Yes, you're seeing I'm firing up Google Hangouts here. And for some reason, if you don't have a split screen and I'm sharing the screen, it shows a screen within a screen, within a screen, within a screen, all the way back. So let me get out of here. So hopefully, no, that's not what I want. I want to start here. A couple announcements. And it's interesting. We start talking about this. With the Linux Labs, it's actually teaching you to have a focus and attention to detail that you probably haven't needed before this. It'll really pay dividends should you go into programming. You miss a tiny little, semicolon, something like that. Of course, the compiler will catch it and tell you have a syntax error, but just tiny little errors that may cause a semantic error. So I'll get into the difference between syntax and semantics here shortly. But we're talking, and quite often I get this. I was working on the Linux Lab late last night. That's a problem. And we get time when we get time. But I'll tell you something. When I was doing my PhD, I'm a morning person anyway. But I would do so much better work in the morning. I would just catch things in the morning. I would literally work, from 6 a.m. to like 11 a.m. At 11 a.m., my brain would be shot. It would just be fuzzy. I'd have to go work out, have lunch. And then I'd get back to work in the afternoon, and I'd only get like 3 or 4 hours of good work. And my brain, again, would be shot. And I'd work out again, and I'd have dinner. And I'd get like 2 hours at night. And after like 7, 8 o'clock at night, that's it. NCAA basketball was like all I could do, okay? So think about this as you're doing your Linux Labs. Quite often, you're going to do much better in the morning. And I know with the school day, things like that, it just doesn't work out that way. But quite often, late at night, we're just not focused anymore to catch these tiny little things. One of the errors was exiting out of Vim. There was a semicolon there, or a colon, and no space, WQ. And we get this, I get this every semester. I'm typing WQ and it won't let me exit. Well, yeah, there's a tiny little colon. And what people often miss is that single dot, for the present directory. So that comes too. Had a question on the quizzes. I know Blackboard has problems. I've known it for a long time. Don't stress. If something goes wrong with your quiz, okay, just email me, okay? I had a problem submitting it. I don't think it's submitted. You can go back on and check it, of course. In Blackboard, in the main announcements, the first announcements, I put a link there that shows you how to check whether you score, but also check your answers. So just do that. Don't stress. Email me. Okay, I can reset it and give you another try. It's not worth the stress. So interestingly, the what colors my dress came up last night, and I heard about that this morning. I don't use Twitter. I'm not on Twitter. Nobody would ever want to follow me or know what I'm doing, so I don't really use it. Yeah, and I don't have time to read what other people are doing. I don't have enough time in the day. So the what color is my dress is coming up. And I guess they're saying if you see it white and gold, you're actually at peace and you're calm. And if you're seeing purple and black, and you just showed it to me and I see purple and black, so obviously I'm not at peace. So I have to reevaluate my life here. So I don't know if other people have looked at that yet. We'll do that maybe on break. Okay, so getting into, come on guys. Okay. Getting into lecture module 5. Of course, lecture module 5 is operating systems, chapter 5, Linux Lab 5. If there's any particular content in this entire course that you should focus on, it's operating systems, okay? Operating systems will really show you what is necessary for a computer and what the computer does. If there's ever time to take notes, take notes. Now, I know that some of you will really go into computer science. Some others will just use this, in other disciplines, which is great. That's all that's necessary. If you're going into security, things like this, if you're really going into computer science, you're going to write down some of the things I say today. They're not in the textbook, and you probably want to research them a little further. So let's see if I can actually get this thing to scroll the right direction. Okay, beginning. We learned that back in architecture, that there were generations of architecture, vacuum tubes to transistors, integrated circuits. And we're going to see that there are generations of programming languages, at least, and the textbook states this. The textbook does not go into that there were generations of operating systems, but there were. with each advance in hardware, and even operating or programming languages, operating systems kind of had equivalent advances. So we can talk about generations of operating systems. And I'll bring that to light, but I won't really focus on it. So as you see, I write, operating system knowledge may be the most important knowledge you can possess. It really shows us what the computer does with the functionality. And I have a question here to illustrate it. Can you have more arithmetic precision with an 8-bit or a 16-bit computer? So I'll kind of put this in light because we think arithmetically, okay? I know that if I have 20, decimals or integers after a decimal point, I have more precision than if I had 10, right? I get more precision. And quite often in computing, we're looking at scientific computing. So it's kind of a trick question, though. Can you have more? And having said that, can anyone answer? Can you have more arithmetic precision with an 8-bit or 16-bit architecture? Neither. I'm sorry. They're the same, okay? Because with software, with the operating system, the functionality is where you really determine that, okay? So it's through the programming. So we know the importance of hardware, okay? It's our architecture, it's our hardware. But the operating system sitting on top of it provides just as much functionality, because I can program an 8-bit, I can write an operating system for an 8-bit machine or a 16, and scientific applications that will have the same precision, okay? So it's the operating system, it's that intermediate software that's sitting on top of that and accessing that hardware, controlling it, that actually gives us most of our, or all of our functionality, especially with what the user sees. Okay, going on. We know the basic model of computation, right? Input, processing, and output. Does anybody recall what is the boot sequence? And first tell me, what is the boot? When a computer boots, what's actually happening? Tell me what the boot sequence is, what's actually happening here. Does anybody recall? Yep. Yep. And what is that? Those diagnostics are actually part of the operating system. The boot sequence, okay, is loading the BIOS, the basic input-output system. That is the core functionality of the operating system. And if everybody recalls, the core functionality, the memory resident portion of the operating system is called the kernel. So that's what happens when I turn on a computer, okay? It jumps to the first instruction, location 0, in read-only memory. And at this point, it starts to read, instruction after instruction. We saw that with the fetch execute cycle. It does a power on self-test, the post. So it's checking memory, it's checking peripherals, things of this nature. And then it loads the basic input-output system. Nothing happens without input-output, input processing output. Bless you. And then after it does executes all the instructions that are in the ROM, it jumps to the master boot record in storage, the MBR, and it loads the operating system, the kernel. Okay, so that's what's actually happening. And recall I asked the question, why is a boot sector virus so bad? Because it's in memory before any application software is there. And of course, the application software, one such example would be antivirus. So a boot sector virus, which lives essentially in the boot sector on a hard drive, gets loaded into memory before the computer has any defenses for it. Okay, so we're beginning to understand why operating system functionality is so important to our knowledge. In fact, security, and we think security with everything. If we're going to secure anything, we're going to see it is the operating system where that security has to be. Okay, let me just see here, lecture captures. So I'm now going to jump to the textbook material. And I have annotated these slides. So there's more on these slides than what is in the textbook. Yeah. So
this virus that gets in before any
boot sector virus. Yep.
Is it at least difficult to make? Because I know people make these viruses.
Okay, viruses in many cases are not difficult to make once you're a good programmer. Quite often, the difficulty is delivering it. Okay, if you think about a nuclear bomb, okay? You can go on the internet and find out how to make a nuclear bomb. Okay, procuring, getting the materials is difficult. But actually what's difficult, you know, getting it into the White House, getting into the Pentagon, getting it to wherever it has to be, delivering it, okay? So, you know, within a few years, everyone here will be able to write a basic virus, okay? Delivering it, you know, getting by the firewall that is in Windows or Mac or something is the more difficult piece, okay? And we'll talk about that when we get to security. So I did want to start, I want to give everyone kind of the big picture perspective of where we are. And recall on day one, I presented that when we learn computer science, quite often we do it from a classification standpoint. So here's where we are. We have the system, and again, I can distinguish between hardware and software, okay? And then going down that software tree, I see I have application software and system software. Today, we're looking at system software. And again, the most conspicuous component or part of the system software is the operating system, but we will look at utilities as well. Next week, we'll look at application software. Okay, so I'm going to kind of jump right into the operating system. Yeah. Okay, I'm going to get to that. Okay, so if you could just hold on, I'm going to present that in just a second. Device drivers interface with the operating system. We think of them as kind of a component of the operating system. Okay, so the operating system. The operating system is the intermediary software between the hardware, computer hardware, and the application programs and the user. Okay, why do we need this intermediary hardware? It performs abstraction. It performs abstraction and multiplexing, which I'll introduce here in just a minute. We need this abstraction. The users need this because the users don't want to deal with, I have to save a file and I'm going to save it on my hard drive and I'm going to put a portion of it here in this cluster and a portion in this cluster and a portion in this cluster. Okay? Users don't want to deal with this. They want an abstract notion of a file, right? I have an MP3 file. I have a movie, you know, .avi, something. I have a Microsoft Word document, which is a file. I think about that big picture file. I don't want to know or have to deal with where it's actually stored across my hard drive and all these clusters that are probably not adjacent or not contiguous, okay? So the operating system is this intermediary software that operates between the hardware and the user. The operating system is also the resource manager. It manages all resources within the computer, and this is necessary. And there are two different types of resources. They're physical resources and logical resources. Okay? Physical resources, of course, I can touch. Okay? The printer here. Okay? The keyboard. Okay? My screen. These are physical resources. An Ethernet port. Okay? So that I can plug my computer into a network. But I also have logical resources. I already presented a file. Okay? In terms of networking, I have network connections. Okay? I have logical connections because you may have a single Ethernet cable into your computer, right? And you can open up a browser. You can open up an FTP client like you do, SSH or PuTTY. You can open up a email client, right? So in this single physical connection that is the Ethernet, single physical resource, I have multiple logical resources. And this is actually what's known as multiplexing. And this is a pervasive concept in operating systems. I create multiple logical resources from a single physical resource. Think about this, okay? I have my computer, bless you, I have my computer up and running, right? But I'm running a lot of programs. I have a lot of programs in memory. Memory is a single physical resource, but I'm running a lot of processes. Remember, a process is an active program, and they're sharing my memory. I have my hard disk, my storage, right? But I have a lot of files out there. I have programs, I have songs in MP3 format, AVI. So I have a single storage system, my hard drive, but I have multiple logical resources residing on it. So we're going to see this concept come up over and over. Okay, so the operating system, two main things I want you to know now. It's the intermediary software between the hardware and the applications or the user, and it's also the resource manager. I won't go into application software. We kind of know what that is. Okay, I did present, okay, again, that there are two types of resources, logical and physical. Logical, again, is something typically that we use. And again, that's multiplexing. Okay, so here's the software stack. So we see at the bottom layer, I have the computer hardware. On top of this, that intermediary software is the system software. And I have operating system and device drivers, okay? And I have the application software. We've seen in our readings, in our Linux readings, and increasingly, you're going to see the functionality of the operating system with the Linux labs. It's going to all start to tie in together. It's going to be really cool, okay? Again, the memory resident portion of the operating system is the kernel. So when I go through that boot process, you know, power on self-test, all this, load the BIOS, jump to the master boot record and load the operating system. When I load that operating system, again, when it's on the disk, it's a program. When I load it into memory, it becomes a process. It is the kernel. It's that memory resident portion. Now, here's a question for you. The operating system is the resource manager, right? If I want to stop someone from copying a DVD, you know, movie, or if I want to stop someone from copying an audio, you know, song from a CD, where does this have to happen? Recall, application software, and again, I haven't presented application software, but we know it, is like DVD burning software, CD burning, whatever you use. Okay, iTunes kind of sits up there. But if I want to stop someone from copying a movie on DVD, where does that functionality, that prevention have to take place? No? The kernel, the operating system. The operating system is the resource manager, okay? Otherwise, they tried to do it on the DVD. They tried to do it up at the application software. I'll tell you a story, and there have been many attempts to do it on many different levels. Sony, this was back in the early 2000s. Sony wanted to prevent people from copying its music CDs. So on each music CD, they put software, essentially a rootkit, that would install itself into the operating system. Because every time you burn a CD, your application, iTunes isn't burning it. I'm going to talk about this later. I really haven't introduced it yet. iTunes has to send a system call to the operating system. It's actually the operating system that burns the CD. Similarly, I'll give you another example. If Microsoft Word, if you hit save Microsoft Word is not saving that file. It's sending a system call to the operating system. The operating system is saving it. If you try to print to this printer, okay, from Word, from your browser, whatever, your browser or Word are not printing to this printer. They're sending a system call to the operating system to print. Why? Because the operating system is the resource manager. This is necessary. If it wasn't like this, there'd be pure anarchy, because Microsoft Word could just write, you know, almost anywhere onto your file system. It could erase your movies. It could erase your songs. Okay, this would be bad. So we need a centralized cop, essentially, to manage the resources. That centralized cop is the operating system. So getting back to Sony, Sony wanted to stop people from copying its music CDs. This is, you know, again, the days of Napster and everything else that was going on. So what they did is on their CDs, they put a rootkit. And I'll come back to that. The rootkit would install itself into the operating system and would prevent the operating system from copying Sony CDs, music CDs. Okay, this actually probably no one would have noticed, except that Sony contracted out to another company to write the rootkit, and there was a security flaw in it. So it actually compromised people's machines. We'll talk about this in ethics, you know, in a few weeks. So imagine you get a music CD from Sony, you want to rip it, okay? And of course it installs into your operating system, and now your system is compromised and it has a new security hole, and people find their way in. All because you bought this music CD. Okay, so that's bad. So Sony was, you know, they went to court, people took them to court, and they won. But I just used a word there, rootkit. Yeah, question?
So it was kind of like a vaccine that just gives people the virus.
Well, no. What this rootkit did is it opened up a hole a security hole, a way into the operating system. So people found their way into the operating system, all right, and they could take advantage of that and gain access to their resources. Okay, but I just used a word there, rootkit. And if you're really into computer science and security, you should write that down and research it. Rootkit, of course, is kind of two words, root and kit. What is root? We've already seen this in Linux. What is root? Super user, right. So a rootkit is a software program that has super user privileges, okay? If you have a program that has super user privileges, right, can do anything, the operating system is the resource manager, it can do anything. Access any part of your file system, take over your computer, do anything, okay? So of course Sony, when they installed this rootkit, but that rootkit had a hole, if someone was able to hack in and find that hole, they had complete authority to do whatever they wanted on your machine. Okay. Now, since I mentioned it, iTunes is sitting up here at the application layer software. There's something else I asked everyone to keep in mind as we look at computer science, that business IT society triangle. We're studying computer science. And textbooks, computer science textbooks tend to focus just on computer science, but we need to look at the bigger picture, okay? There's actually a company out there that kind of navigated this in terms of digital rights management, DRM, songs, movies, things of this nature. They were actually able to ensure or provide confidence to the music industry and film industry that, yes, we can deliver your content and it will not be ripped off. Apple, iTunes, okay? Because, okay, the operating system, again, is the resource manager. So if you want to prevent someone from ripping off your music, your movies, whatever, you have to put that functionality into the operating system. What is Apple? Apple's big brother. It is so controlling. But there's kind of a positive aspect to that. So they were able to go to Hollywood, able to go to the music industry and say, listen, we have this tightly constrained system, okay? No holes whatsoever. We control everything. We control all the software on it. So from the iTunes up to the application layer all the way to the operating system, everything is tightly woven. So they went to the music industry and said, we can ensure that through iTunes, we can deliver your music by the internet and people will not be able to share it. Now, there are a few little workarounds, and we won't get into those. So as we look at computer science, though, we do have to think about that big picture. Because of Apple's reputation and their controlling, need to control everything, they were actually able to broker this partnership with the music industry and the film industry. So it's not just computer science. We need the computer science to understand what's going on, but we also need to look at that bigger picture. Okay, so too much information beyond the text. Here's the answer, the question to the device drivers. So what we see, of course, at the lower level is the physical resources, okay? Everything above that, we're starting to look at logical. When I say logical, what am I looking at? Data, programs, okay? Device drivers are tiny little programs, okay? And they serve as an intermediary between the operating system and the end hardware devices. Why do we need them? Well, there's no way, and I'll just use Microsoft as an example here. There's no way for Microsoft to know what devices you're going to hook up to your system, right? Say a printer, Lexmark printer, Canon printer, HP. And it doesn't make sense, and they will include drivers, of course, and there are now generic drivers. But it doesn't make sense to put all of these into the operating system because then you have a nice big bloated operating system, okay? So it's this device driver that provides the intermediary between the device itself and the operating system. So on one end, of course, the company is, HP writes their device drivers. Lexmark writes their device drivers. Canon, okay? Now there is some other work by the operating systems. Linux, for example. There's a big community in Linux writing device drivers. So HP, for example, will write the device driver to control the printer, but what it will present upwards, so to speak, to the operating system is this common interface. So the operating system uses the same calls to write to a Canon printer, to an HP printer, to a Lexmark printer, okay? So what I have is that common interface. And I might as well present an example, a great example of the common interface, point down to the wall here, the 3-prong plug, okay? So what I'm now talking about is standardization. And we need this in computer science, right? Think about if you went to Target, whatever, and you bought a toaster, and on that toaster they had a 4-prong outlet. You come home, you try to plug it into your 3-prong, electrical outlet in your home. Obviously, it's not going to work, and we'd be pretty pissed, right? So we need the standardization. We need the standard interface, okay? And that's what the device drivers do. They provide the standard interface to the operating system, so the operating system can use the device. Yeah.
That's why it makes it easy that everyone has an iPhone, because everyone has the same charger. So if you don't have a charger, then someone else's charger.
Well, yeah. I didn't know quite where you're going with that first, but yes, I'll take that. Now, also, the operating system provides a standard interface to the programs themselves. So Microsoft Word asks for a page to be printed in exactly the same way as, say, your web browser. If you go to your web browser and go up into File and say Print, okay, it's sending the same system call to the operating system. And I'll give you one more example of why device drivers, why we have this architecture, why this architecture is necessary. Do we have any idea what's coming down the pipe? So say when Microsoft writes their operating system now, what, 2015, do they have any idea what devices will be out there in 2017, 2018? We don't have a clue, right? So how are we going to provide for this future-proof functionality? Okay, well, through system calls and, of course, the device drivers themselves. So if some new, completely new product device comes out, that manufacturer, all they have to do is write a device driver so that it interfaces and provides that same consistent interface to the operating system. And I forget, how many people here are taking programming logic right now? Outstanding. You're actually seeing this software interface already, right? Whenever you import, have you imported something? Okay, you're importing a library and then you're using something that someone else wrote, okay? And as long as you are constrained or follow those interface standards, how do I call that specific method and what are the arguments, okay? That is a software interface. So by the way, does anybody recall the 3 types of interfaces in a computer system? 3 types of interfaces. Well, think about this. When I talk about these, what are these? Devices, physical, okay? If I move up to device driver, operating system program, they're logical, they're, no, same thing. I was just kind of lead you on there too. Okay, software, okay? So I have physical interfaces, my Ethernet port. I have software or logical. The last would be actually human-computer interface, HCI, okay? When I walk up to this computer, keyboard, right, display. So really I have 3 basic classifications of interfaces within a computer system. Okay, now, operating system. I'm presenting operating systems from a lot of different directions or dimensions here. When it comes to operating system design, it's always going to be a balance or a trade-off between convenience and efficiency. Okay? People, users, want convenience, right? Apple, iOS, iPad, things like that. People don't want to deal with a command line interface. If we only had command line interfaces, we would not have many computer users. People would not overcome that learning curve, okay? I think I presented this, the technology acceptance model, the TAM, okay? Technology acceptance model is based on 2 things, perceived usefulness and ease of use. If something's easy to use, everyone will use it if it's useful, okay? If it's not easy to use, well, a certain percentage of the people will overcome that learning curve and still use it, okay? Here, we're budding computer scientists. We would overcome that curve and we would even, overcome the challenges of a command line interface. Yeah, Apple and Android. But my mom would never use a computer if she had to use a command line interface. Just not going to happen. But recall, I started this by saying it's always a blend between convenience and efficiency. As I add more and more convenience, the system as a whole will become less efficient. Why? Well, think about, the Microsoft computer here, okay? I have a nice graphical user interface. That's a lot of code. It's a lot of programming. Where is that to be run? Where does all processing take place? In memory, right? So as I get this wonderful graphical user interface, it's consuming more and more memory. I have less and less memory to actually run real applications. And of course, we accept that on the desktop, but what about a server? Okay? Servers quite often only have a command line interface. Why? They're being run by, of course, system administrators. They're completely comfortable running command line interface. And if I have no graphical user interface consuming memory, my web server can be entirely efficient, right? All of its available RAM is dedicated to what it needs to do, which is deliver web pages. There's also a bit of a security enhancement if I don't have a graphical user interface. Everyone here now has gotten into the Linux labs. Think about that. If you only had a command line interface, what are the chances you could walk up to that computer and do something useful? Are you just off the top of your head going to imagine, oh yeah, ls? ls is a natural name to list the contents of a directory. No, I wouldn't get that, okay? Move, mv, copy, cp. You're not just pulling these out of thin air, right? So with a command line interface, there's actually kind of built-in security, at least for the general user. No one's walking up and actually doing anything useful on it. With a graphical user interface, I can walk up to any Windows machine, Mac, whatever, and go straight to the file system and start poking around. Okay, so there is a security aspect there as well. Okay, so I've covered most of this. Let me just read and make sure I've covered all of it. Yep. See if I can scroll the right direction. Okay. The operating system. Now, when we start talking about the operating system, there are major modules in the operating system. What does the operating system have to do? It has to control processes, has to control memory, has to control storage, the file system, has to control devices. So now we're going to start looking at the various components of the operating system. Okay. The operating system does manage network connections. Now, in a minute, we're going to look at, there's certain things known as a network operating system, or short NOS. Okay. Linux is a network operating system. Out of the box, Linux is a network operating system. Mac, with its essentially Linux kernel, is a network operating system. Microsoft Windows is not, right? On Mac or Linux, SSH, we don't have any Mac users here right now, visible with computers open. SSH is built into the operating system. I can open up a terminal. Terminal is built into my Mac, okay? And I can SSH my username at acadnx, hvcc.edu. SSH is built into the operating system. What did you have to do? What do we have to do with Windows? We had to download PuTTY, which was an SSH client. So it's actually not a core component of the operating system. Microsoft Windows is not a network operating system, okay? It has networking functionality, but it's not a network operating system. Now, as soon as I say network operating system, there's another concept that is implicit here. With a network operating system, we can, of course, go peer-to-peer, but quite often we're talking about a client-server environment. So when I talk about a web server and the things that we get, application server, all of these things, email server, okay? So inherent in these network operating systems, I could very easily move to a client-server environment. In fact, the Mac Mini makes a wonderful server. You can get these things off eBay now, the older ones, $200, $300. They are fantastic web servers. I wouldn't say much more than that. So the operating system manages network connections, okay? Again, it is the resource manager. It's going to manage processes, memory, the file system, and devices. And those are actually the four big components. Okay, so what were those again? It manages processes, memory, the file system, and devices. And we understand the distinction between a process and a program. I install a program. Where do I install it? On my hard drive. It's a passive entity, right? Has no resources. When I load the program, execute it, it becomes a process, and then the process has resources. So say I have Microsoft Word on my computer here, and I double-click its icon. Well, of course, right now Word is sitting on disk. It's an installed program, installed application. When it comes into memory, I just said the first resource, it gets some memory from the operating system. The operating system allocates memory. And then the operating system will start to run it. It'll start allocating some CPU time to it. Now, of course, Microsoft Word without being able to work on a document is useless. So it'll open up a file for you to edit. That file is a logical resource. You may want to email it to someone, okay? So again, Word is going to ask the operating system to open a network connection, email, whatever. Okay. So file management. Now, we're actually seeing this again with Linux now. The file is a logical resource for the user, right? I think about my song.mp3, a movie, .avi or whatever format, MP4. The operating system has to keep track of it. Remember, it's that intermediary device of where it's actually located on disk, what clusters. So the operating system will maintain a file table. Okay, that's the data structure, which indicates where everything is. And in Linux, and we'll get to this in a minute, you've actually seen this. When you do an ls, what does ls do? It lists the directory contents. Where do you think it's doing? It's going to the file table, pulling that information, what is in this directory, and presenting it to you. When you do a move in Linux, okay, move again, you're actually keeping the same file, just changing its name. What's actually happening? It's just updating the file table. It's changing its name. When you do a copy, okay, CP in Linux, which keeps the existing file where it is, but makes a new version, it's actually going to create a whole new entry in the file table for the new file. It's going to copy the name, give them whatever name you gave it, and then allocate space for it. Okay, a couple things here not in the text. Files are viewed in the hierarchical format. That is in the text. I have something up here, JL. Don't use my documents. What do we think about first with everything we do again? With everything we assess, what do we think first? Begins with S. Sounds like security. Security. Okay? It's a real tough one there. Think about this. Let me give you an example. What if in every house in this country, everybody kept their valuables in the same place? You're a thief. You break into a house. You know that. I open the front door. I turn right. I walk 3 steps. Here's a closet that says my valuables. Empty it out. Go to the next house. Walk in the door. To the right, 3 steps, my valuables. Where does Microsoft store everything by default? My documents, right? If you don't choose where it's going to save a file, for the most part, if you're writing something, there are exceptions here. We won't go into keychains and things like that. It's putting them in my documents, right? How are people hacking into your system? People are not hacking in one by one. I'm not choosing you as a target. It'll happen with a big, the NSA, something like that. You're writing a program, right? So if I'm writing a program and I can get into your computer, right? I want to choose something, of course. I know what that file is called. I can hard code that into my program. Go to my documents, grab everything, right? This is what Microsoft has actually done. They've actually created a convenient place for thieves and hackers, right? It's like that house. If every house had a security closet where you keep your valuables, your jewelry, and everything was right inside the front door, thieves would have a very easy time. They wouldn't have to ransack. What do we have? We have that exact situation here. So my recommendation, don't use my documents. Don't do it. Create some other directory, however you want to name it, your own directory structure, and save things there, okay? Because even if you think that there's not important information there, there actually is, okay? And I'll get into that when we get into security and privacy. Because nobody is out there is writing a program that's going to test, what did you name? I have no way to guess how you name your directories, okay? So again, I recommend you don't use My Documents. And Apple kind of does the same thing. But Apple's a Linux operating system and just implicitly is more secure. And there are a few reasons for that. I also use the term in Linux, namespace, okay? Space for names. Namespace is a space for names, okay? I introduced this in Linux. The difference is, of course, if we look at a single directory, and a lot has to do with the operating system, you look at Microsoft Windows is not case sensitive, right? So James with a capital J is the same as James with a lowercase j. So that namespace is kind of constrained. Very different in Linux and Mac, of course, which is Linux, which is case sensitive. So James with a capital J, if I named a file James with a capital J and James with a lowercase j, these are actually two different files. So a namespace is all permissible names within whatever that namespace is. Quite often it's within the directory, right? I can have a file with the same name as a file in another directory. Why? Because I can distinguish between them through the path, that hierarchical path that is the file system. But within one directory, I cannot have two files with the same name. Why? It's ambiguity. The computer cannot deal with, we cannot have any ambiguity in computing. I always need to be able to make a choice, okay, a decision structure. So when I talk about namespaces, I'm talking about the permissible names within a particular, say, or a set of identifiers within a directory, okay. So I actually presented already what are the Linux ls move commands doing. So here is, a picture of the Windows operating system, okay. And again, in Windows, they call things folders. They kind of renamed it, where it's really directories in the Linux world. And I did just add this to the Linux file system because we're going to start moving around within Linux, okay? So when you log into Linux, everyone's directories are right here. So if you did this, okay, if you're through up to where we should be in Linux, if you did a CD up to the upper directory, parent directory, you saw everybody's home directory. And of course, they're all in homes, okay? I could go CD, space, dot, dot again, and move up to the root directory, at which point I'd see the et cetera, devices, the homes, the users, var. You're probably going to see a binary too, bit, okay? And I did list, I just added what these are, okay? So et cetera are my configuration files, okay? Device, of course, is devices. Home is the user directories. User are the user binaries, okay? And there could be subdirectories live. So when you execute a command ls, cp, mv, right? These are commands that you can use. Those executable programs are down in user. Again, you'll probably see bin too, binary, which will be system binaries. Okay, those are the components that are actually loaded into the that comprise the kernel, loaded into memory. That is the operating portion of the operating system. And then variable is just system data that's written during execution. You can see how simple this is. Okay, I have no Windows registry, although I kind of have some kind of functionality for that in various places. But it's a much cleaner, I guess, more elegant approach to the system configuration for the operating system. Okay, tell you what, before I put everyone into zone sleep here, good place to stop. Let's take, I have 9:15, let's take 10 minutes, and 5 and 9.